Okay, so what I want to do now is talk about how to understand vector spaces in kind of more detail. So let's begin with V a vector space. For example, we've looked at kind of a bunch now. I mean, we've got Rn. That's kind of our prototypical vector space, is the one we've looked at most. We've got kind of continuous functions, real-to-real functions. That's a vector space as well. I can add and scale and multiply. And what I'm going to look at quite a bit today is polynomials of degree at most n with real coefficients. Oh, maybe also I should just include all polynomials too, I think. It's probably a good idea. So that's all polynomials without any restriction on the degree. So what I want to do first of all is introduce some terminology which we've already seen for Rn, but I want to extend it to an arbitrary vector space. So let's fix a subset, a finite subset of my vector space, V1 to Vp. So if I take a vector of the following form, so up to lambda p Vp, where these lambda i's are in the real numbers, then this is, well, first of all, what is it? It's just a vector. It's a new vector in V. This is a linear combination. So this is exactly the same terminology as we used when we talked about linear combinations of vectors in Rn, totally identical. So it's a linear combination of the vectors v1 ... to vp. Okay, so definition. So this lecture is going to contain a lot of very important definitions. I'd recommend watching it slowly, going through it many times, because many of these definitions, it's really crucial you have them down. Some of them are going to be repeats, but some of them are going to be quite new. So first of all, the span of v1 to vp is exactly what you think it is. It is the subset of all linear combinations of v1 to vp. It's exactly the same definition as when I was thinking about vectors in Rn. So just as a quick example, in a more interesting vector space, if I was to talk about the span of, let's say, sine of x and cos of x inside CR, for example, so continuous real-to-real valued functions, so I'm thinking about these guys as in continuous functions from the reals to the reals. What is this? This is the collection of all linear combinations of these. Well, that's all things of the form lambda 1 sine x plus lambda 2 cos x. So it's all of those sitting inside all continuous functions from the reals to the reals. Just as a quick example. We say that the set v1 ... to vp is a spanning set let me write that more neatly, is a spanning set of V if the span is equal to V. So everything can be written down as a linear combination of the elements v1 to vp. So we've seen a few examples. We've seen quite a few examples, really. We know how to calculate them, at least in Rn. But here's a really important one. E1 ... to En. That set sitting inside Rn. Everything can certainly be written down as a linear combination of these. Now this is going to be something we're going to return to a little bit later on, but that's a good example. Another example, maybe in the space of polynomials, if I take the polynomial 1x squared ... up to xn, that set, well, every polynomial could be thought of as a linear combination of these. I mean, that's kind of what a polynomial is. So that means what? This is a spanning set of polynomials of degree at most n. Okay, so it's exactly the same basic idea as for Rn. It's just we've talked about it for a general vector space. Exactly the same type of constructions. Here's an important fact, and I'll leave this as an exercise. It's a really good exercise. Span of V1 to Vp, well, it's a subset of V in general. It's a subspace. So that means it contains 0, it's closed under addition, and it's closed under scalar multiplication. That's a really good exercise. I would advise you to definitely do that. Right? So it's the same kind of thing as when we were checking if the kernel or the range of linear transformation were subspaces. You need to check the 3 defining properties of being a subspace. So they're not so bad. For example, I mean, the 0 vector is definitely in the span because I could choose lambda 1 to lambda p to be all 0, which guarantees that 0 is a linear combination. Okay, so here's an important definition coming from span. We say V is finite dimensional. Finite dimensional if there exists a finite spanning set. In other words, I can find a finite set V1 to Vp such that the span is the whole thing. If not, so if we cannot find a finite spanning set, we say V is infinite dimensional. Now, in this course, overwhelmingly, we're going to be looking at finite dimensional vector spaces, but it's important to understand that that is a restriction. So just as an example, e.g., I mean, I've just told you, Rn and Pnr, those both have certainly finite spanning sets. I've written some above. So Rn and Pnr, these are finite dimensional. Because I can literally write down a finite spanning set. It's a bit more difficult to show something as infinite dimensional because you would need to demonstrate in some way that there is no finite spanning set, and that can be quite hard. But I think it's believable that the following are not finite dimensional. So if I take all continuous functions from the reals to the reals and all polynomials without any restriction on the degree, these are infinite dimensional. That's quite hard to show. Certainly the continuous functions is pretty tricky to show, but the polynomials, that's not so hard. I think I'm going to leave it as a homework exercise. So the tough thing about that is showing that no finite set could possibly span. And for polynomials, here's a clue. I mean, if you did have a finite spanning set, there'd be some sort of maximum degree among the elements. And any linear combination of things can only ever drop the degree of the polynomials involved. So that means you can't possibly get all polynomials if you have a finite collection spanning, or a finite collection when I'm taking linear combinations. It's kind of subtle. So overwhelmingly, we're going to be looking at finite dimensional vector spaces. Okay, so first of all, this is kind of funny. I've defined the concept of finite dimensional, but I've not defined the concept of dimension. And we kind of have an intuitive feeling for what dimension means, but I think the question arises, I mean, if we are finite dimensional, I mean, what is the dimension? I mean, what does that even mean? What does dimension mean? It's kind of a cool question. Dimension is one of these things that's kind of fuzzy in people's brains. You kind of know what 2-dimension means. It's kind of like a plane. 3-dimension means 3-dimensional space. And then when you go to 4 dimensions, you start to think about time and your brain starts to fold. And then 5 and 6, apparently that's just something crazy physicists think about. But I think we're going to come up with a much more elegant way of thinking about dimension. So how do I do this? Well, first of all, let me introduce kind of another side to this story, one that we've already seen and isn't obviously related to this question, but definitional. So tons of definitions today. So this is going to basically be a repetition of what you've seen before in Rn, but I've got to do it in general. So let's take V1 ... to Vp. Another subset of V we say is linearly independent. Shortened to Li. This is if and only if, well, it's exactly the same condition as before. A linear combination is equal to 0. This is if and only if lambda 1 is equal to ... lambda p, all equal to 0. So the only linear combination which gives you the 0 vector is the trivial linear combination where every single coefficient is 0. Okay, so the non-version of this, the negation, is linear dependence. So I'm going to write down what that means explicitly as well. Vp and V is linearly dependent. Again, written NLD. If and only if, so it's just the negation if it's not linearly independent. But explicitly what that means is there exists lambda 1 ... to lambda p, not all 0, such that this linear combination is 0. So it's just the negation. Linear dependence is not linearly independent. Okay, so just as a quick example, because we're used to seeing this for Rn, we have techniques for checking it. We kind of write some sort of matrix, row reduce it, that kind of thing. Well, it makes sense outside of Rn. Let me just give you a quick example. If I take the set sine x, cos x inside continuous functions, this is linearly independent. Now let me show you why. I think it's quite a good idea for me to prove this, to illustrate what you need to do. So what I need to do to show linear independence is to show that if I do have a linear combination equal to 0, the coefficients are 0. So first of all, let's assume lambda 1 sine x plus lambda 2 cos x is equal to 0. And before I do anything here, this is an equality of functions. When I write something like this, what I mean is this linear combination is equal to 0 for all values of x. So it's an equality of functions, and 0 here is the 0 function. So that's a really strong condition. You see there may be one specific value of x where this works, for some specific lambda 1 and lambda 2, but that's not enough. I need it to be equal for all values of x. So let's do the following thing. If this is true, let's divide through by cos. So there are lots of ways to do this. If I divide through by cos, I get tan x here, plus lambda 2 is equal to 0. So let's think. Imagine if lambda 1 was not equal to 0. This would imply that tan of x was the constant function minus lambda 2 divided by lambda 1. You see I need lambda 1 not to be 0, so I can divide through by it. And this has to be true for all x. But that's impossible, because that would be saying tan is the constant function. This is not the constant function. It's not the constant function, so this is a contradiction. So what does that mean? Well, the contradiction is assuming lambda 1 is equal to 0, so non-zero. So lambda 1 has to be equal to 0. If lambda 1 is 0, well, this thing gets knocked out, so this gives lambda 2 is 0. So this implies lambda 2 is equal to 0. What does this imply? Well, it implies a linear combination is 0 if and only if the coefficients are 0. So this immediately tells me that sine x, cos x inside CR is linearly independent. This is a good example. It's going to turn up later on when we start to think about differential equations. Okay, so let's think about a few properties of a collection of vectors which are the same as linear dependence. So I could prove these, but I don't really have time. So we're going to take them as facts. You've seen me kind of prove these to some extent for Rn. The general proof is exactly the same. So if I give you V1 to Vp linearly dependent, so that means there is some lambda 1 to lambda p, not all 0, such the linear combination is 0. Turns out this is if and only if Vj is in the span of the other vectors. Dot, 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 to, let's say, Vj minus 1, Vj plus 1, Vp. For some j. Doesn't need to be true for all of them. We've seen examples of that kind of in Rn. But for some j it has to happen. And I tell you what, this is a really cool... You can kind of reinterpret this in a really cool way. What that actually means is the following. It means the span of the other vectors, when I remove one of them, is the same as the span of all of them. So what that means is, in a linearly independent set, there's at least one vector you can throw away, in this case Vj, and the span remains the same. It's a really important property of linear dependence. So I'll say that one more time. A linearly dependent set has the property that I can remove a vector and it doesn't affect the span. The span is the same, I don't lose anything. So just as a quick example, if I took the span of, I don't know, 1, 0, 0, this is in R3, 0, 1, 0, and 2, 1, 0. Well, notice this guy is in the span of the others, so I don't need it. I can throw it away when it comes to the span. So linearly dependent sets have the property there's kind of unnecessary vectors in them when I'm talking about the span. Okay, so why have I told you stuff about this? Well, this is all building up to a reasonable definition of dimension. So here's a super important definition. Fundamental definition. So again, let's have V. Let V be a finite dimensional vector space. So remember that means? That means there's a finite spanning set. So for example, Rn or PNR, that kind of business, a finite spanning set. So a basis for V is a subset V1 dot 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 to Vp such that two things hold. The first is it's spanning. So the span of V1 dot 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 to Vp is equal to the whole thing. And the second thing is it's linearly independent. So V1 dot 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 to Vp is linearly independent. So a basis equals a spanning linearly independent subset. So it's a subset. It's not a subspace. A basis is just a collection of vectors with this important property. So it's two things happening at once. So it's saying you can get everywhere, and it's also saying all the vectors are kind of going in completely independent directions. Remember, linear independence intuitively should be thought of as your vectors are kind of totally independent directions in a sense. So let's do some examples. The most important example is in Rn, E1 to En. So that's 1, 0, 0, 0, 1, 0, 0, all of those. These are the columns of the identity matrix if you want. This, in Rn, is a basis. You span, and they're all absolutely, definitely linearly independent. This subset is called something. It's called the standard basis for Rn. It's a very important subset. Okay? Not a surprise it's called standard basis. You use it when you define the standard matrix of a linear transformation from Rn to Rn. Another example, what about polynomials? Well, actually already written it down. 1x, x squared, dot, 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 to xn. This guy, that's also a basis for Pn. Remember, a polynomial is 0 if and only if the coefficients are all 0. That's kind of the definition. And a linear combination of these is 0 forces all the coefficients to be 0. So this definitely is a linearly independent spanning set. Here's a more exotic example, one that if you have done 1b you'll be familiar to. We will kind of do it at the end of the course, but it's worth pointing out. If I take the subset sine x, cos x, in the set V, where V is the solutions in CR to the differential equation y double prime plus y. If you remember, just doing something silly there, equals 0. If you remember back to your 1b days, this is an example of a homogeneous linear second order differential equation. And if you remember, to solve this, you go through the process of finding two independent solutions. In this specific case, sine x and cos x are examples. And if you think about it, what does that mean? Well, all solutions are linear combinations of these. So this is very intriguing. So this subset is a subspace. That's a vector space in its own right. And this subset is a basis of this vector space. Okay. Pretty awesome. So this idea is really, really important, the idea of a basis. We're going to think about bases kind of a lot over the next week or so, but I want to point out some kind of standard facts about bases. The first one is, and this is an easy one to get confused about, bases are not unique. They're very, very not unique. Just example, I'll just do something in R2. We've got the standard basis 1, 0, 0, 1. But we've also got other options. In fact, if we think about it, any collection of two linearly independent vectors also works. So here's another example. They certainly span everything. You could do that by writing a matrix and reducing it. But these are both bases for R2. So a basis is any subset which is linearly independent and spanning. There are tons of options. In certain cases, there are ones that are very canonical, ones that really stick out in your face, like in Rn, there's the standard basis, or for polynomials, there's kind of 1 and x squared, dot, dot, dot. But in many cases, there aren't kind of completely obvious examples of solutions or examples of bases which jump out at you. That's going to be a big part of the theory. Okay, so just to recap, we have the concept of a spanning set. That is a subset, V1 to Vp, which spans the entire vector space. So that means the span of V1 to Vp is equal to V. If you have a finite spanning set, you are finite dimensional. Next, we've got the concept of linear independence. Same definition as linear independence for Rn. It basically means, being linear independent means that they're all traveling in independent directions. No one can be written as a linear combination of the others. Okay, linear dependence means that at least one of the vectors is in the span of the others, which means I can throw away one of the vectors in the span and it doesn't affect it. And finally, a basis is a subset where both linear independence and spanning happen simultaneously. So I've given some examples, but I've not justified that, for example, bases exist. For all I know, there's an example of a finite dimensional vector space where there's no example of a basis. Who can say? So I'm going to introduce 3 really important general facts. Some of these are easier to show than others. All of these are going to apply to V finite dimensional. if you're not finite dimensional, life is much harder. So finite dimensional vector space. First fact. If V1 to VP is a spanning set of V, then it contains a basis. Now, intuitively, why is that true? Well, if it's linearly independent, it is a basis, so you're done. If it's not, it's linearly dependent. That means one of the vectors has to be the linear combination of the others. That means I can throw away one of the vectors and get the same span. The span is still V in which case. So I can keep doing that, throwing away unnecessary vectors until eventually what happens? Well, eventually I would have to be linearly independent. And at that point, the span has remained the same because every time I've thrown something away, the span has been the same V. I would have a linearly independent subset. That means it's a basis. So this fact basically relies on this fact here. It's this. The fact that if it's linearly dependent, I can throw stuff away and keep the span V, and eventually it has to stop when I'm linearly independent. Okay, so just as a quick example, to make sure we're not going completely crazy, let's do it in R2. If I have 1, 1, 0, 3, 1, 0, 1, that's definitely spanning. Definitely spanning. Everything can be written as a linear combination of these, but it contains the basis. Well, actually, any choice of two of them will be a basis, it turns out. But I'll choose that. That's contained in it's a basis. Why? It still spans all of R2, and it's definitely linearly independent. Okay, that's the first fact. Second fact, this is harder, but kind of equally intuitive. If V1 to VP is linearly independent, then it can be extended to a basis. So what I mean by that is I can keep adding vectors until eventually I have a spanning set and it's still linearly independent. That's much harder to prove formally, but let me just give you an example. E.g., I don't know, I'll do it in R3, 1, 2, 0, 0, 1, 0. That's linearly independent in R3. What do I need? Well, if I add, I don't know, 0, 0, 1 to it, I think that gives me a basis. Of course, this would require checking, but I'm pretty certain that this is a basis. So adding that extra thing is a basis for R3. So the basic idea behind this one is, if V1 to VP doesn't span, take a vector which is not a linear combination of V1 to VP and add it to the set. That's still linearly independent. If it's the whole thing, you're done. If not, repeat the process. And you keep doing this until eventually you hit V. And the hard part of that is knowing that at some point you have to be guaranteed to hit V itself. Right, so that's the difficult part of that, and that actually relies on the next statement. The basic idea is, if you're a spanning set, you contain a basis. If you're linearly independent, you can be extended to form a basis in potentially many ways, but you can be extended. Okay. C, and this is kind of the most important. If I take V1 to VP, linearly independent, and let's do another collection of vectors, U1 dot 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 to UK, spanning. This implies that P is less than or equal to K. So linearly independent sets are always in smaller than or equal size than spanning sets. That is a really, really fundamental result. It's quite difficult to show. It's actually called the Steinitz exchange lemma. It's really clever, but it's a brilliant general fact. So linearly independent sets are of size less than or equal than spanning sets. Okay, so I'm going to use, so that's much harder to show. I think A and B are quite intuitive. C is quite difficult to see why, but we're going to take it as a fact. Okay, so I'm going to use this to prove some pretty fundamental results. First off, theorem. Any finite dimensional vector space has a basis. Ooh. Crucial, right? Now, for the ones we gave, Rn, Pn, we could just see one immediately. But we weren't completely certain that it's always possible. So here's the proof. It's pretty simple now. Let's just choose V1 to Vp, a spanning set okay, well then what do we do? Well, we could just apply A. What does A say? A says, well, it contains a basis, so you're done. So the finite dimensional means there is a spanning set. That's what finite dimensional means, is a finite spanning set. So now, by fact A, it contains a basis. Awesome. That was kind of easy. Here's a much more kind of deep result. Theorem. This is a truly awesome result. I think you'll agree when you see it. So let's have V be a finite dimensional vector space. Any two bases. So remember, there are infinitely many bases potentially, but any two bases have the same size. That is such an important result. So two bases, they could be completely different, but they have to be the same size. Let's just go back to the top here, my examples. Here, I chose bases for R2. That's got size 2, that's got size 2. They're different vectors, but they still have the same size. So this is a really deep result. Well, it's not really deep, but it's a really fundamental result. And the proof is brilliant, and I want to show it to you because it's super elegant. So let's imagine I have two different bases. Now V1 ... to Vp and U1 ... to UK be bases for V. What does that mean? Well, it means they're both linearly independent and they're both spanning. So first of all, from one perspective, this is linearly independent and this is spanning. So what does that mean? So this implies, by my fact C, that P is less than or equal to K. Linearly independent sets are less than or equal to spanning sets. Well, we could turn that on its head. They're both linearly independent and both spanning. So exactly the same thing turned around. I could just take this, move it around. Well, what does that mean? Exactly the same logic says, by C, K is less than or equal to P. So I've got two numbers. I've got inequalities in both directions. There's only one option. P is equal to K. So this fact C is really brilliant. It gives rise to this incredible result. Two bases automatically have the same size. Definition. So I remember when I learned this first, this was the first time I realized the incredible power of this approach, because suddenly we have a brilliant definition for something that was fuzzy before. So again, let's have V be finite dimensional. Be a finite dimensional vector space. The dimension of V, denoted dim V, is the size of a basis. Now, if I had said that before, proving this result above, that wouldn't make sense, because in theory, two different bases might have different sizes, so this wouldn't be meaningful. But we now know that two bases have the same size, so this number, this size of a basis, is a fundamental invariant of a finite dimensional vector space. It is the dimension. Now, why is that a really sensible definition of dimension? Well, what does dimension mean? Intuitively, it means the number of different independent directions you need to go in and still be able to go everywhere. In R3, you need 3 directions completely independent from each other to go everywhere. For R2, it's 2. This is a really crisp encapsulation of that idea. Right, so a basis is a set which can go everywhere and all the directions are completely independent. So let's just check that this makes sense logically. So examples. Well, what do I know? What's the dimension of Rn? Well, let's do this properly. We need to find a basis. Let's choose the standard basis. The standard basis is E1 up to En. How big is that? It's of size n. Rn has dimension n. Thank God. If that were not correct, we'd definitely have the wrong definition here. What about the dimension of, let's say, Pnr? So it's easy to get this wrong. You might think that it's going to be what? N. Well, it's not quite, because what's a basis? A basis is 1x ... up to x to the n. And that has what? N plus 1 elements. So this is not n, it's n plus 1. Easy to make a mistake there. Brilliant. Let's do another example. Let's take V, a subspace of R3, so let's do the plane in R3, which containing, well, the origin, 0, 0, and let's do 1, 0, 0, and let's do 1, 1, 0. So let's think about this. So remember, a subspace, so all of this can be applied to subspaces as well. Remember, a subspace of a vector space is a vector space in its own right. So you can talk about the dimension of a subspace, right? Because you just find a spanning set which is linearly independent, but it may not be a spanning set for the whole vector space, it's just a spanning set for the subspace. We'll see an example in a second. But this is a good example. So V is kind of a subspace of R3 because it's a plane which contains the origin, but let's first of all think about it in terms of spanning. Well, V is the span of the vectors 1, 0, 0, 1, 1, 0. Yep. So I've got a spanning set immediately. These two vectors. Is it linearly dependent? Well, absolutely. If you were to write this down in kind of a matrix and do row reduction, it's basically already reduced. We definitely know 1, 0, 0, 1, 1, 0 is linearly independent. So what does that mean? This means the set 1, 0, 0, 1, 1, 0 is a basis for V. That implies what? The dimension of V is 2. Exactly as you'd hope. It's a plane. You want it to be two-dimensional. So if you think about it, what's a line? Well, a line is something where the basis is just a single element for the basis. That's what a line has always been. It's been something which is generated by a single vector. So that means the basis is size 1. It's just a vector V such that the line is lambda times V. Brilliant. Okay, so this is an incredibly good definition. It makes something very fuzzy in our minds totally concrete. When you hear the word dimension now, forevermore, it means something precise. It is the size of a basis in a vector space. That is what dimension means, precisely. So, let me introduce a few more kind of intuitions that are worth saying. So, some important facts. Again, V is finite dimensional. If V is not finite dimensional, you can do some of this stuff. It's just quite a bit more difficult. It's the kind of thing you'd do in a more advanced linear algebra class. You'd perhaps do it to some extent in 110, but really it'd be kind of approaching the graduate level. So don't worry too much is what I'm trying to say. So important facts. Here are some cool things. So first of all, let's trace some information around. Well, if I have V1 to Vp linearly independent, well, what do I know? I know by B that I can extend this to a basis. And a basis is of size equal to the dimension. So this means P has to be less than or equal to the dimension. So if you have a linearly independent set, it has to be of size less than the dimension. If you have a set which is bigger than the dimension, it is automatically linearly dependent. Okay, another way to think about this is, well, let's do spanning. Let's do V1 to Vp, spanning. So what do I know? Well, property A that I wrote above, or fact A, tells me every spanning set has a basis. So that means what? It has to mean P is bigger than or equal to the dimension of V. So said another way, if you have a set which is of size strictly less than a dimension, it cannot span. I think that's intuitively obvious. In R3, you can't have two vectors spanning all of R3. This is a precise version of that. So, final thing is if I have P is equal to the dimension. So this is really neat. If P is equal to the dimension, then we have the following awesome equality, or equivalence. If I have P equal to the dimension and a subset of linearly independent things, well, let's just think about this. If it's linearly independent, it can be extended to a basis, okay? A basis of size dim V, it's already got size dim V. That means it has to be spanning. So this has to be a basis. So that means it has to be a spanning set. Now let's go backwards. Well, if V1 to Vp is a spanning set, and P is the size of, is the dimension, well again, spanning sets contain a basis. Okay? But if you've got size equal to the size of any basis, that means you have to be a basis yourself, which means you have to be linearly independent. So this is if and only if. So there's this sweet spot. If I'm talking about a subset of vectors, at the dimension, linear independence and spanning are completely equivalent to each other. If you are below the dimension, you could be linearly independent but not spanning. If you're above the dimension, you can be spanning but not linearly independent. So it's this kind of beautiful sweet spot right in the middle where the two concepts become the same. So the conclusion of this, I think, is the following. This is the kind of thing you're going to have to sit and think about it for a while. A basis is equal to a minimal spanning set. So that means a spanning set of smallest size possible. So I can't throw anything else away and keep the span. It's also equal to a maximal linearly independent set. Two different ways of thinking about it. So a basis is kind of the biggest a linearly independent set can be. It's the smallest a spanning set can be. And the beautiful thing is it completely matches up perfectly. Let me just point out why this is all super familiar to us. A familiar example is good old matrices, right? So let's take n vectors in Rn. So this is linearly independent, if and only if what? Well, if reduced A, where A is the matrix A1 ... to AN, so that's an n by n matrix, right? Has what? A pivot in every column. Is that right? Yep. Well, this forces it to have a pivot in every row. Pivot in every row. And what does that force? that forces it to be spanning. This is a spanning set. Ooh. Brilliant. So this is this brilliant fact, right? At the dimension, linear independence and spanning become completely the same. It's a fantastic result. And it's kind of a fundamental fact of kind of all of mathematics, this idea of a vector space having a dimension where these two things completely match up. It's a really beautiful idea. And it's great that we can see it like really concretely in the Rn case. We've already seen this phenomenon by thinking about row reduction, but it's true in this much more general setting. The moment you're finite dimensional, so admit a finite spanning set, bases exist, they all have the same size, it's called a dimension. Linear independent sets have to be size less than or equal to it, spanning sets are size bigger than or equal, and at the dimension, the two concepts are completely equivalent. So the final thing I'll say today is, on this lecture, is the following result about dimensions of subspaces. So as I said before, I mean, this is all talking about the dimension of a vector space V. If I give you a subspace of a vector space, it itself is a vector space. So I could talk about the dimension of the subspace just thinking about it as a vector space in its own right. For example, in R3, that's three-dimensional. But I could take the subspace, which is a plane, just like I did a moment ago, that's two-dimensional. So the following kind of comforting result is true. So again, let V be a finite dimensional vector space. And let's have U inside V a subspace. So that's a subset, which is a subspace or vector space in its own right. First of all, then U is finite dimensional. Exactly as you'd hope. It would be crazy if it wasn't. It's actually quite hard to show, but it is definitely true. And not only that, exactly as you'd expect, the dimension of the subspace is less than or equal to the dimension of V. Just like a plane inside R3, it's 2 dimensions versus 3 dimensions. And as a quality, so if the dimensions are equal, this is if and only if they're equal to each other. So U is equal to V. So proper subspaces, ones which are not equal to V, always have dimension strictly less than the dimension of V. So that's kind of hard to show. What is true, I mean, if you know you're finite dimensional, showing the dimension is smaller is not so bad, because what you do is you just take a basis for U. It's definitely linearly independent, because it's linearly independent in V, and then you extend it to a basis for V. So that means a basis for U could be extended to a basis for V, and that's the reason the dimension is less than or equal. The hard part is showing that you're definitely finite dimensional. That requires a bit of work. But yeah, this is brilliant. So the key takeaways from this video are: a finite dimensional vector space is one where there is a finite spanning set. So that means there's a finite collection of vectors such that everything can be written as a linear combination of those vectors.